Right, in part two of the gas laws, we're going to be focusing on still using the combined gas law, but we're going to be manipulating it a little bit differently than in part one. So at times, we actually want to hold one of our variables, either pressure, volume, or temperature, constant so we can observe just how the other two variables affect each other. We're going to use that combined gas law, but we're simply going to remove whatever variable is being held constant. So our first law is Boyles' law. This is when we're going to hold temperature constant so we can view the relationship between pressure and volume. So when we remove the variable held constant temperature, we just have our pressure times volume is equal to our pressure times volume. So as pressure is increased, we find under Boyles' law that the volume will thus decrease. This means then that pressure and volume under Boyles' law affect each other indirectly. As one goes up, the other one goes down. So a graphical explanation of this, you can see here at the bottom of your screen, is that as pressure increases, as you go left to right, we can see volume is thus decreasing, and we have this indirect relationship between the two. And we'll go over some real life examples tomorrow in class. Now, a calculation that involves Boyles' law would be the following. A sample of a gas occupies the volumes of 2 liters at STP. If the pressure is increased to 2 atm at a constant temperature, what is the new volume of the gas? So here we have a constant temperature, so by removing temperature, we have our pressure times our volume. We're going to input our variables that are given to us in the word problem, including the fact that STP provides us the 1 atm, our standard pressure that we're starting at. And then by multiplying and dividing, we get our new volume of 1 liter. All right, our next is Charles' law. This is where we're going to hold pressure constant, and by doing so we find that as temperature is increased, volume thus increases as a result. So temperature and volume affect each other directly. As one goes up, the other one goes up. As one goes down, the other one goes down. We can represent this graphically by using the following chart to show this direct relationship between temperature and volume. As temperature increases, volume also increases. So example of Charles' law is the following. A sample of a gas occupies a volume of 5 liters at 300 Kelvin. If the temperature is doubled under a constant pressure, what will the new volume of the gas be? So our constant pressure allows us to remove pressure from the combined gas law. We're going to input the variables that we know, the 5 liters and 300 Kelvin. We said that temperature was doubled, so we double that to 600 Kelvin. What is our new volume of the gas going to be? And by cross multiplying and dividing, we get 10 liters. So we can see here specifically that as temperature is doubled, volume also is doubled from 5 to 10. And finally, we have the Gay-Lussacs Law, which in this case we hold our volume constant. So this would be like a rigid container that we would be using. And we find by removing volume and keeping it constant that as the temperature is increased, pressure is also increased. So temperature and pressure affect each other directly. So here again we can represent, I didn't put on here the graphical representation, but you should have an exact same graph as the volume and temperature one to show that direct relationship, and I'll check in with you about that tomorrow. However, our one example to show the setup is the following. A 10-liter sample of gas in a rigid container that's giving us the fixed volume. At 1 atm and 200 kelvins is heated to 800 kelvins. Assuming the volume remains constant, what is our new pressure? So here again we've removed volume from the equation. We've inputted our variables as such, and by cross multiplying and dividing we get that our pressure is 4 atm. You can see that as we quadrupled our temperature, we also have quadrupled our pressure, and thus again leaving volume constant. All right, so again, we've talked about 3 different gas laws where each of the variables is held constant, so we can observe the 2 variables that we're interested in. And these all are combined to form that combined gas law that's on the last page of your reference tables. And again, remember, this combined gas law allows us to solve problems of pressure, volume, and temperature. We just hold our number of particles constant. All right, so just remember that none of the gas laws depend on the identity of the gas. We're simply looking at pressure, volume, and temperature. Okay, that's it. We'll continue with these calculations and look at some real life examples tomorrow in class.